Hello everyone, this is Academia on Demand. I'm Josh Myers and I'm bringing you the second video of the theory section. And today we will be talking about the periodic table and exactly how all of these things we are going to come to know when we're referring to them in any sort of way with molecules, with compounds, any sort of thing, what we're going to come to know as the elements, the fundamental components of all of that stuff I was just talking about. And so the first periodic table, this organization of exactly how the elements fit together, and we'll talk about how they were organized, it was done by Dmitri Mendeleev. And he organized them by atomic mass. And so it always starts with hydrogen. Hydrogen has an atomic mass of 1. Hydrogen has an atomic mass of 1, and actually, using very sophisticated equipment, they can tell it is approximately 1.0079 something, but that doesn't matter, it's 1. It's 1, and these are in atomic mass units. It's 1 atomic mass unit. And 1 atomic mass unit, that is because it is a single proton. A single proton with a very, very light electron orbiting the nucleus. Next, we move on to helium. Helium is an atomic mass unit of 4. Atomic mass unit of 4, and this is because it has 2 protons and 2 neutrons, and these combine to come to about 4 atomic mass units when you account for the idea that protons and neutrons are approximately the same mass. And so then you keep counting. We are going to say lithium has 3 protons and 3 neutrons, and that beryllium has 4 protons and 5 neutrons. And this sort of neutron-proton sequence starts to become pretty, not necessarily always uniform. There will sometimes be more neutrons than protons. But as a general rule, we can always say that the number of protons will always increase as you go from left to right by 1 each time. So hydrogen will always have 1 proton, helium will always have 2 protons, lithium 3, beryllium 4, boron 5, carbon 6. Carbon is very special, and we will talk all about carbon in a later video. Nitrogen 7, oxygen 8, fluorine 9, and neon 10. And so this is why a man named Moseley decided to organize the periodic table. This whole organization couples things together very nicely by the number of protons, what he came to call the atomic number, and the way that I most like to talk about the periodic table, the atomic number. The atomic number, and this is just simply the number of protons. What is very interesting about this, it tells you a lot of information. It tells you not only the number of protons, but in any atom of a single element, the number of protons, P plus because of the positive charge, is equal to the number of electrons. And this is very important if you're ever wanting to draw any sort of Lewis structure. You want to know how many electrons, specifically how many electrons are in the valence, and we will talk about that very, very soon. So these elements, the fundamental units for making molecules, for making compounds, they cannot be broken down. You can't take a fluorine and cut it in half. Well, you could, but there'd be a massive nuclear holocaust explosion. So they cannot be broken down into anything further. These are the building blocks for everything. We will talk about with bonding later. And so the reason, why is the periodic table, do you think, why is it organized the way it is? Well, this is very much dependent on the electrons. So this is group 1. The group label will always be referred to for vertical rows. Vertical rows are groups. This is group 2, this is group 3, 4, 5, and so on. And this And the horizontal labeling, hydrogen, helium make up the period 1. Period 1, period 2, lithium, beryllium, and then this whole business. Period 3 and period 4. And so before I talk about what's down here, let's explain exactly why this is all really important. So let's group 1. Group 1 will always have the one valence electron in its outer energy level. As we know from the last video, Niels Bohr came up with this idea of energy levels. So in the first energy level, this first period 1, and the periods represent the energy level being referred to. So the first period represents hydrogen, helium, and hydrogen and helium have electrons only in the first energy level. So I guess we're just starting with the period now, and then we will explain how it applies to the group. So in the first energy level, let's draw this nucleus. I'm going to have a hydrogen for now. And then around this nucleus, around this nucleus, we are going to have one electron. And because remember that the number of protons is equal to the number of electrons. And so there's only one energy level, there's one electron in that one energy level when you're talking about hydrogen. Now for helium, there's also only one energy level, but this time it's containing 2 electrons because it has 2 protons. It is atomic number 2. Number of protons equals number of electrons. But this time we also talk about how it's atomic mass number 4, which means that it has 2 protons. We know that it's atomic number 2, but it also has 2 neutrons. And so this first energy level, it has 2 electrons. The reason why the periodic table is organized this way is because when you move to lithium in period 2, a new energy level is started. The first energy level is full with 2 electrons. And that is my very sloppily drawn period 2 energy level. So second energy level. And now this energy level, if you count the number of elements, just simply count them. You got lithium, beryllium, that is 2, boron, carbon, nitrogen, oxygen, fluorine, and neon, that is a solid 8. And so these 8 elements, they add an electron each time, and they come to fill this second energy level. Of course, the nucleus increases by 1 proton each time and 1 or 2 neutrons each time, and thus will come to make that atom's structure. And so why this is all important is because all of the elements in group 1 will have just 1 electron in what they call one valence electron. And what this means is that in their outermost energy level, in this, for instance, in the period 2, the lithium atom, the outermost energy level, the second energy level, will only have 1 electron in it. Hydrogen, the outermost energy level, the first energy level only has 1 electron in it. And now sodium, Na, the third energy level, its outermost energy level, because of the period number 3, will only have 1 electron in it. You got it right there. And so that is very important when we'll talk about bonding later. This is very much a skill building video. This is very important, very applicable for any sort of solving of problems with bonding or with this thing we're going to talk about called ionization. Very big word, very simple meaning. We got to get used to it. It is very important. And this idea of valence electrons applies very strongly to this idea of ionization. And so now I just want to talk a little bit about what is ionization. Ionization happens when the element loses an electron. So it goes minus an electron, subtracts an electron. And what happens is when this operation of losing this electron happens, when this is a lithium, or no, let's make this simpler. Let's erase for a second. Let's erase this rule we have here. We have practiced this rule lots. Let's put it back now. It's the number of electrons. If this is a helium, this is a helium atom. This is helium atom. It's 2 electrons, 2 protons, 2 neutrons. If an operation happens where you get rid of an electron, this idea of this electron not happening anymore, it's not there, it's somewhere else, walking its dog or something. It is somewhere else. There's only 1 electron instead of 2. There is supposed to be 2. Does it just blow up? It does not. What happens is it becomes helium plus, helium plus. And what this means, this is what ionization is. It takes on a charge, because as we know, electrons have a negative charge. So if it loses a negative charge from its normal structure, this means that inversely it becomes positive. And that's how I like to think about ionization. And so this is a really important idea, because it also has an inverse idea. What if this was just hydrogen? What if this was a hydrogen atom and it had the 1 proton and the 1... Did I move you? No, you are still seeing what I am doing. And the 1 proton. And so what if an electron that was lost by the helium, the helium that just lost the electron, that electron flies through space, empty space, the very mysterious thing physicists like to talk about all the time, and lands right in the orbital of the hydrogen atom. And this hydrogen atom accepts this electron. This electron, now it has 2 electrons surrounding a single proton in the first energy level. So it would become what is referred to, instead of hydrogen plus, instead of gaining a positive charge, because it gained an electron, electron is a negative charge. It's a negative charge, negative. That means that it will also gain a negative, because adding a charge to a stable atom, it will take on that charge. And this is the difference between adding and subtracting. Before, when you had the helium, it lost that negative charge, it gained the positive. So I just really wanted to reiterate that idea, because it can become confusing if someone has not practiced this sort of thinking of losing and gaining a charge. So now that's over. We've talked about the ionization. We will do a couple of practice problems with exactly how many neutrons, protons, energy levels, electrons, all that sort of thing, so we can really identify exactly what these elements are in a sort of a notation, a sort of way that we can uniformly talk about exactly what element we are referring to later on. But before we do that, one thing that I want to do is I want to highlight a couple of groups that will be of particular interest to us when we move on through this crazy maze we call chemistry. So the first group other than hydrogen, and that's why hydrogen is by itself, because it's a problem child, it's a little bit different than everyone else. But lithium, sodium, potassium, and many more, such as rubidium, cesium, and francium, which I did not write here because my board is limiting me, and I'm sad. But these elements that I just listed are called the alkali metals. And they are very reactive for reasons we will talk about when we get into orbitals. But for right now, we know they are called the alkali metals. Alkali. And that group 2 metals, the beryllium, the magnesium, the calcium, they are called alkaline earth metals. So earth metals, earth metals. And so on the left side, period, groups 1 and 2, as well as these elements that start down here, they start on the 3rd period, and they connect magnesium to aluminum. Horizontally, they are referred to as the metals. This is the alkali metals. These are the earth metals. Group 2 is the earth metals. And finally, these ones in the middle that are listed down here, those are called transition metals. And they will be very interesting for us to talk about later on when we talk about catalysts. And now when we move closer to the right side, we've got our what we call these special things. They are called metalloids. And in this, let's get another color. We need another color to help us out here. Let's get green. And so green, and what the metalloids are is they are essentially, they share properties, and we will talk a lot about properties. They share properties of both metals and non-metals. And this is exactly how we'd identify metalloids. There is a staircase, a lovely crystal staircase down from the heavens of boron down to the element that we call At, and it is very far down here. If you extended it all the way down, it would probably reach the bottom of my board and go off the board. But it is a staircase. You go down one to the right, down one to the right, and these elements, again, they aren't really sure whether they're metals or non-metals. They do a little bit of both. And now, finally, to the right side, we have the non-metals, the ones that, if you were to just talk about what we know of metals, they aren't that. And that might seem obvious, but as we come to understand chemistry further, we will come to know a lot about why non-metals are special rather than just not metal. So, as we move closer to the right, we got the non-metals. And finally, we get to group 7, and these are called the halogens. The halogens, and this is another reason that they are labeled, is because they are extremely reactive. And that, when I talked about with group 1, they are extremely reactive. They like to give away electrons, while group 7 likes to accept electrons. And that's why when they bond, when they do this thing we will talk about later called bonding and making molecules, group 1 and group 7 like to be together. If molecules had feelings, they would be very happy together. And then finally, we talk about the group 8, the noble gases, the Sir Noble gases, and they have a full outer valence electron shell, C number 8. The outer valence energy level will always be full, and that's why they are called the most stable elements, because they do not, there's this idea where if the elements are always trying to gain a full outer energy level. And so when, for example, lithium, or one of the group 1 metals, because they only have one valence electron, as we discussed earlier, they will ionize relatively easier. They will lose an electron relatively easier, because they want relatively easier compared to beryllium, to magnesium, because they want to get a electron configuration just like the noble gases. So sodium wants to become just like neon in that perfect world where, again, elements have feelings. And so this is the idea that I'd like to leave you with, and we will now just perform a couple of practices to make sure we understand exactly how we are getting the number of electrons from the number of protons and all that sort of interesting stuff, because we cannot do chemistry if we do not understand this very important skill. It's a very important skill. So let's just do one. Let's do sodium. So sodium, so 23, and this is a special kind of notation I'm using, and I will tell you all about it. And Na, and I'm going to put a plus right here. And now what is this notation? This 11 represents the atomic number. And what does the atomic number represent? It represents the number of protons. So right away we can write down it has 11 protons. 11 protons. Now. This 23, that represents the atomic mass units. And we know the atomic mass units, the number, the 23, that is the sum of the number of protons and the number of neutrons. So we have the number of neutrons plus the number of protons is equal to 23. Well, we know that the number of protons is 11, so therefore NO is equal to 23 minus 11. Let's do some math here, and we got 12 neutrons. Now finally, if we wanted to find the number of electrons, we know that normally, without this, let's erase this for a second, if we didn't have this plus here, we didn't have a charged sodium, we would say that the number of protons is equal to the number of electrons. So, but because there is a charge here, what does that mean again? What it means is that it lost an electron. Now has the same electron outer shell configuration as neon, as this stable noble gas. And so it had 11 electrons, it lost one, now it has 10 electrons. 10 electrons. And so now this is a very systematic approach. Remember, we have atomic mass units, AMU, and then the atomic mass number, and then finally we have the charge. And so whenever we see any notation like this, we know exactly what to do. So now this video is very, very long, so I'm going to have to leave you, and I will see you next time, and we will talk more about these things we call elements. Talk to you later.